Hello guys, welcome back to another Ming Tech Media tutorial. Today we're going to be discussing another vital and very important algorithm within computer science, the Quicksort algorithm. Now I'm going to outline a couple key points to note about Quicksort. I'm going to go through a demonstration, show you how the partitioning works in Sketch. I'm going to just draw up a nice little diagram so you can have a visual representation of how the algorithm works. And then we're going to go over to Eclipse and, code it out in Java so you can see how it works when you actually program the algorithm. All right, so let's get to it. So what is Quicksort? Quicksort is a divide and conquer algorithm. And just as an aside, just like in my merge sort video, I said you should be familiar with recursion before trying to, learn Quicksort and time complexities as well, at least on a basic level. That holds true for Quicksort as well because it works and operates in very similar ways. So before you progress to do this video, I would expect and hope that you're familiar with recursion and time complexities and asymptotic analysis on a basic level. All right, back to Quicksort. Yeah, so Quicksort is a divide and conquer algorithm which uses recursion to continuously divide the array into sections, making the problem smaller at each successive function call. So when a function is placed on a stack, right, with Quicksort, there's going to be an overall problem, right? And then it's going to break the problem down by after getting, a partition index, which I'll show you later. It partitions the array into left and right sides, and it recurses to the left all the way until it gets to its minute part, solves that problem, gives the answer to that problem back to the function caller, pops that function off the stack, and continuously does that until the whole left side is solved, then recurses on the right all the way down the recursive tree to its smallest problem, gets the answer for that problem, and pass that answer back to the caller, which then pops off the stack once it's done, and then so on and so forth until we have all these answers for these problems, these sub problems that were divided by Quicksort, and they keep getting passed back up the chain until we get to our overall problem that we're trying to solve. And then once we have these answers, we're able to return them back to the original function, and it's able to solve because we solve that overall problem because we've solved the problem in smaller parts. And you'll see this and it'll start to make sense. Partitioning. Partitioning is done in two ways, right? There's two types of partition. There's the Lomuto's partition, which we'll discuss here in this tutorial, and the Horus partition. They both kind of look alike. They both use pointers to progress through the array and perform swaps. Horus partition uses pointers at the pointer at the front and the back of the array, or the beginning and the end. And Lomuto's partition usually has two pointers that start at the front and progress through the array. So yeah, I'll show you the Lomuto's partition in this tutorial. And stability. What do we need to know about Quicksort in terms of stability? Well, Quicksort is not a stable algorithm. So what does that mean? It doesn't preserve the order of duplicates, unlike merge sort, which does. So the duplicates in merge sort, they appear in which the order that they came in the input array. So time complexity. In terms of time complexity, Quicksort runs in O of log n time, nlogn, and that's because you're iterating at every level and at every call, or at every level you're having the array, and then you're doing linear work at every level. So when you have the array, that's log n, and then when you do iterative work at each level, that's n. So that's why it's an nlogn algorithm in the best and average case. Now in the worst case, it is O of n squared, and you'll very rarely see this or come about this in like the wild, or when you're using it, but that's if an array is almost completely sorted or it has a lot of duplicates. So if there's like an array with 10 elements, and then of those 10 elements maybe 5 of them are 4s, that has a lot of duplicates. So Quicksort might operate and degrade to an O of n squared algorithm or time complexity in that sort of case. Or if you have an array that's almost completely sorted, like if the numbers are almost completely sorted, then the efficiency of quicksort in terms of time complexity can degrade to an O of n squared algorithm in that case. All right, let's talk about in place. So quicksort does not need any extra space, unlike merge sort that allocates extra space for the auxiliary array, which the merge happens in. So therefore, quicksort is an in-place algorithm. And as you can see here in this tutorial or in this slide, I have like kind of made the more important terms red, just so you can remember them. Just, you know, so you can remember the key important parts about quicksort. And in terms of real world implementation, it's used to sort primitives. And it's the underlying implementation of arrays.sort in Java. So arrays.sort in Java, it works on primitives. And if you like right click and sort of look up the implementation of arrays.sort in Java, which you can do in Eclipse and IntelliJ or NetBeans or whatever IDE you use for Java, you'll see how it's coded, and you'll see that it's a version of quicksort. If you know the quicksort algorithm, I think it like uses timsort, which there's these variations of these staple algorithms like merge sort and quicksort that people have modified and used within programming. And arrays.sort is that. And then, like I said, it works on primitives, and quicksort it lends well to, you know, working with primitives. All right, so I'm gonna open Sketch and we're gonna like draw up a diagram of how the partition works and how the quicksort algorithm works in general, and then after that we'll go into some code. All right, stick with me. Hey guys, we're over here in Sketch, and as you can see, I've already sort of drawn out an array. It has 7 elements, and on the top of it, I've labeled it with the indexes from 0 through 6. I've labeled the low and the high, which is n-1 for high, which is at the 6th index, and 0, the low is at the 0th index. And I've outlined on the right all the steps for partition here, and also there's different ways to select the pivot. But before I get into that, I just want to remind everybody that for this partition, we're using the Lomuto's partition. There's 2 ways to partition in quicksort. There's the Horus partition, and there's a Lomuto's partition. And for this tutorial, once again, this is Lomuto's partition. All right. So there's different ways to select the pivot. Many people select like the first element. Other people calculate the middle element and use that as a pivot, or select the high. For this purposes of this tutorial, and to keep things brief and simple, I'll select the high element. So we do that by you know, doing something like int pivot. This is just more or less pseudocode, but in Java, my language of choice, you do like int pivot is equals to array high, right? So as you can see, our pivot would be 3 here, which is in the 6th index. And let's take a look at these steps here, right, for partition. So the first thing we're going to do here is we're going to select a pivot, right, which we've done. We've selected a pivot. We've made our pivot array high. Then we initialize I and J, right? Those are going to be our pointers. J is just going to help us iterate through the array. I is just going to keep track of the boundary of the last index that is smaller than the pivot, and you'll see that because essentially what we'll have is we're going to have 2 sections, right? We're going to have 2 sections, and I'll draw it out here really quickly. Let me just make a better drawing. So we're going to have 2 sections, whatever. Let me just try and use this ruler really quick. So yeah, we're gonna have a couple sections, right? Let's draw this here, right? Our sections are gonna be everything that's less than or equal to the pivot on the left side, and everything that's greater than the pivot on the right side. So we'll have 2 sections here: everything that's less than or equals to the pivot, and everything greater than the pivot. And basically, we're going to perform swaps. And when we are iterating through the array, we're going to use I to keep track of the boundary of everything that is less than or equal to pivot. So the I is going to sit like here, right? And as we progress through the array, depending on whether or not we find elements that are less than or equal to the pivot, this section is going to grow. So it's going to be less than pivot or equal to pivot. And this is going to be greater than pivot. And our pivot is going to be like our last element. So this is going to be like the piv. And then once we're done with that, like once we've created these sections and we've completed a full iteration, we're just going to swap these two. We're going to swap I plus 1. So we're going to need to, since I is keeping track of the last number that is less than or equal to the pivot, is keeping track of that boundary, we're going to need to go to I plus 1, which is like the next element. And then we're going to need to swap array high and I plus 1. Right? So basically, we iterate through the array and we check if array j is less than or equal to pivot, right? So j is going to be our iterator. And if it's true, if that condition holds true, we increment I and then we swap I and j. And when we finally break out of the loop, like I said in this example, or like I illustrated in this example, what we're going to do is we're going to swap I plus 1 and high. And then we're going to return I plus 1 because that's going to be the index of our pivot our pivot when it's final sorted position. All right. So let me just erase this and continue with this example so this can make sense. So select another color here. All right. So we're going to have, here we're going to have I. We're going to set I equals a low minus 1, right? So we're going to have I here, and then we're going to set j equals to low. So that's going to be, array 0, and this is going to be low minus 1. I is going to be low minus 1, so that's going to be minus 1, right? So as we start to iterate through this array, right, we're gonna try and check to see if our condition array j is less than the pivot. Remember, our pivot is 3. So our pivot is 3. We're trying to check to see if array j is less than that. So we're gonna keep iterating. So j is gonna go here. It's gonna go to the 7. And we're gonna check that condition, and that's not true. So we're gonna iterate to the 4. Again, we're going to check that condition and it's not true. Then we're going to iterate to the 1, which is in the third index, right? So we're going to see that 1 is less than or equal to the pivot. So what are our steps here? We increment I and then we swap I and j. So let me just make some room here. Let's erase this. So now we're at the third index here. And we need to increment I. So I is going to go to, instead of being minus 1, it's going to be 0 when we increment it. Then we need to swap I and j. So we're going to swap the 11 and the 1. So we're going to swap that, erase that here. So now 1 is, so now we have 1 here and we have 11 here, right? So now we're going to continue to progress through the array, right? So we're going to go to the 9. That condition is false. We're going to go to the 6 and that condition is false. And so we're done iterating, right? So we're not going to check it against this condition here, against like the last element. We're iterating up until the n-1 position where the 6 is, right? So, or the high minus 1, sorry. So we're iterating up until the 6, all right? Or the element right before the high. So now when we break out of that loop, what we're going to do, what's the next step? We're going to swap I plus 1 and the high, right? So I plus 1, this is I plus 1 right here. It's I plus 1. This is I plus 1 right here. And this is high here. As we can see, it's labeled high. So we're going to swap those two. Let me just erase. So we're going to swap. We're going to swap these two. We're going to swap I plus 1 and a high. And you'll see after this, the array will start to look more sorted. So let me just erase these things here. 7, 3. So the 3 comes here and the 7 goes here. And as you can see, it starts to look a little bit more sorted. You know, we've basically sort of bubbled all the small elements to the left and the larger elements are on the right. So now if you take a look at the 3, right? If we take a look at the 3, it's in its final sorted position. Everything to the left of it is less than it. Everything to the right of it is greater than it. So in terms of this array that I've, this example, it's in its final sorted position. So we now return I plus 1, which is this array 1. So we return array 1. Sorry about the handwriting, guys. It's kind of hard to work on these like tablet pad things. Yeah, but you get what I mean. So everything, so like this, so you see how we iterated we did the I plus 1 to get outside of this boundary here, where everything is less than it, where the 1 is the only number in this this boundary that's less than a 3. So we incremented I once we broke out of the loop, I plus 1, and we swapped it. We swapped it with array high, which is the pivot. And so the pivot was 3 formerly, and now it's in its final sorted position. So we're going to erase all this, and then we're going to continue with our example, but now our 7 is going to be our pivot. So let's do that. Let's start all over. We're going to initialize I to be low minus 1 and J to be low. And 7 is our new pivot. And we're going to see if there's any numbers that are less than or equal to the 7. And if there are, we're going to swap them with I and J. So we check 1 here. That is less than or equals to our pivot. So we increment I, and then we would perform an in-place swap. And we increment J, and then we're going to see that condition is true again. So we increment I, and then that's just an in-place swap. The same thing happens with the 4. We increment the I, we do an in-place swap. Then we iterate the J. Oops. Then we iterate the J. This is false. 11 is not less than or equals to 7. So we increment the J again. That condition is false with a 9. Then we increment the J again. But then we see a 6 here. So we see that that condition is true. So we increment the I. Now I is going to be at array index 3. Now we swap the array index 3 and the array index 5. So basically the 11 and the 6 are going to be swapped. So let me just erase this. And then I'm going to swap the 11 and the 6. So 6 comes here. 11 goes here. So now we go to I plus 1. So this is the I plus 1 here. This 9. I plus 1 lines up with that element here. And then we swap that with the array index at high. So the pivot, basically. Array high and a 9, the I plus 1, we're going to swap that. So that's going to put the 7 in its rightful position. And we're going to see, again, those boundary conditions are satisfied where the 7 is in its final sorted position. So everything to the left of it is going to be less than or equal to that, and everything to the right of it is going to be greater than that. So we swap the 7 and the 9, and usually everything on the right won't be sorted. So we're gonna, just leave that alone for now. But you see how everything to the left of 7 is relatively sorted. It's sorted, it's sorted. And 7, that was our second pivot. The 3 was our first one, but the 7 is our second pivot. It's in its final sorted position. Again, those boundary conditions are satisfied. So we're going to erase this. And then we're going to start over with 9 as our pivot. All right, so we have 9 as our pivot, and we have I already initialized to low -1, and then J is initialized to low. So we're going to iterate through this array again. So J, is that equals to, oh, sorry. What we do first is we check the first index. So that's going to be true. So we increment I, and we swap an in-place swap. We do an in-place swap, essentially. Then we increment J again. That's going to be true. And we do an in-place swap. After we increment I, we do an in-place swap. Increment J again. That's going to be true. So we increment I, do an in-place swap. We increment J again. Need to increment I, do an in-place swap, and so on and so forth until we get to 11. And that condition is false, so the I doesn't move, it stays where it is, right? So now we've broken out of that loop, right? And now this 11, the fifth index, so this I plus 1, that's, we go to the I plus 1 the next, because the I is at the fourth index right now. The I is right here. This is where I is. This is the fourth index. So we swapped I plus 1 and the high. High is 9, so we swap these two. So let's swap that. And as you can see, once we perform the swap, this array is now sorted. Everything, you see how everything is now in its final sorted position. So when we did that swap, the boundary conditions are satisfied. So for this 9 here, everything to the left is less than or equal to the 9, and everything to the right is greater than 9. So that's why we needed to do that I plus 1 and then swap it with the I, right? And then we just return I plus 1, and that which is this fifth index, and that gives us the value there. So we return, in this case, we would return array, array 5. And that's basically how the Lomuto partition works. We're going to replicate this in code, and you're going to see how this works in Java. All right, stick with me. Okay, guys, so we're back. I'm here in my Eclipse, and I'm in a package, algorithms.solution, and I have a class that I've named Quicksort. Okay, there's a couple methods that I want to emphasize that we need to work on. So there's the partition method, and there's the actual quicksort method, which has the recursive code. And then there's a swap method. And a swap method is just going to be something that takes in your array and plays values and swaps those values. So let's code all that out. Let's code all that out and see how that comes out. So I'm going to start with the partition method, right? And first I'm going to do public static void, and this is just a method signature. Oh, sorry, not void, int, because we are returning an int. We're returning the final sorting position of the array. I mean the element, the pivot actually. Sorry, I just need some water. Ooh, throat's kind of dry. So yeah, so we have an array here. This is one of the arguments you can pass, or parameters, int low and int high. And let's keep going. And in this method, what are we gonna have? So basically what we're gonna do is we're gonna select the pivot, and the way I'm gonna select the pivot is by selecting the last element. So I'm gonna do int pivot equals to array, or sorry, nums high. And actually I'll just name this array because it's easier in most tutorials, and I do that. So I know I said in the example in Sketch that we're going to start off the pointer variables for, well, we're going to start off at low -1, but that can be confusing because at the end, because of the low -1, you're going to have to do the I plus 1 in the swap. So to avoid that, we just set I equal to low, and that should solve that problem. And also there could be some funky stuff in the code when you try and work that out and sort that out. So I'm just gonna have my I equal to low, just for simplicity's sake. So you know, you won't have to also do that I plus 1 swap with the high. So I'm gonna have int j equals to low as well, and j is less than high, and j plus plus. And inside this, what we want to do is we want to swap nums with I and j, and then we want to increment I if we find that nums j, or sorry, array j is less than or equals to the pivot. So if array j is less than or equal to the pivot, what we want to do is we want to perform a swap, and we haven't coded that out, but it's pretty simple, on I and j, right? Ignore the error for now. We're about to code that up. Forget the semicolon, and like I said, we increment I. And we jump out of this loop. What we want to also do is swap. Remember, we need to take the index at high, or the element at high, and switch with I, because I keeps track of the boundary of all the numbers less than or equal to the pivot. So we need to switch those out. We need to switch the pivot and put it in place in between that boundary where the numbers end, where that the numbers that are less than or equals to the pivot end, and where the numbers greater than the pivot begin. So we're squeezing it in between those boundaries. So that's why we have to perform that swap with I and high. So I'm going to do that array I and high. I, comma high. All right. So semicolon. And then what we want to do is we want to return I, and that's your partition method. So we're going to code up the swap right now. Pretty simple. We just do public static void swap. And what this takes in is it takes in your int array and int pause 1. I'm going to name it pause 1, and int pause 2.
Right, so what happens is we create our temp variable, int temp, and we set it equals to array pause 1. And then I'm just gonna, we're going to take the array pause 1, and we're gonna set that equals to array pause 2. And we're going to do the opposite here. Well, not really the opposite. We're just going to take array pause 2, and we're going to set it equals to temp. And that's your swap. All right, so, okay, we're getting an error here. Is low, J, okay, it's supposed to be a semicolon. There we go. Okay, so we've coded up the swap. We've coded up the partition method. Now let's code up the actual quicksort method. So that's just going to be public static void quicksort. And it's going to take in an array, int low, and int high. And for this method, our base case would be if the low is less than the high. And basically, if that is false, we reached our base case, which means that the boundaries for the pointers have crossed each other. Because remember, these things are dynamic. They're changing every time, because as you recurse down the left and the right side, you're splitting these arrays and these values are changing. So we're using pointers to sort of keep track of that, right? So we're going to recurse down the left and the right side and then return these answers back up the function call stack. So basically we need to get our pivot index. So we're going to say int p is equals to partition, and we are going to do array low and high. And then after that, what we're going to do is we're going to quicksort on the left and on the right. So copy that, quicksort, and it's going to be from array low, comma, p minus I. I mean, sorry, not p minus I, p minus 1, and then quicksort array, and then p plus 1 and high. And basically what that does is, for the first one here on line 28, what that does is it recurses from the low to the high. And these are the new, like I said, this changes with each successive call. So this is another call of quicksort, with low being the new low. Well, it hasn't really changed. And p minus 1, which is the pivot index minus 1. So the element right before it, you're recursing on that side. And then the element right after it will be the low for the next call, right? And then high, it will remain the same. And then these successive recursive calls will keep on happening until we solve each incremental problem and return them back to the callers. So we've got the partition, we've got the swap, and we've got the quicksort. One other method, which, you don't really need it, but I just want to be able to print out the code. I'm going to do a print array method. So bear with me. I'm going to do public static void print array. And it's going to take in an array of integers. And what we're going to do is we need to first find a length. So int n is equals to array.length. Okay, length. And we're going to have a for loop. And we're going to set int I is equals to 0. I is less than n. I plus plus. And for each call, what we want to do is, well, I don't really need these brackets. What we want to do is we want to do system.out.println L. Well, just, well, what is this? What is this? Well, we won't do print line. Let's just do print. And we want to print the array index at I. And then we want to concatenate a little space. And once that's done, we're going to do a system.out.print line. And yeah, that's just going to be blank because we just need the extra space. Sorry for the honking. I live in New York City. It can get kind of loud sometimes. And then we need our main method as well too, so we can test all this out in our main method. So what I'm going to do is I'm going to create our driver program. And for that, what I'm going to do is I'm going to do public static void main string args. And then in this main method, what I want to do is I want to create an array, right? And we're going to initialize the values really quick. Let's just say I want to do 10 to, let me space this out, 10 to 7. What else? 18, random number 9, 1, 5, and a 6. And that's our array. And then we're going to do int n is equals to array.length, right? And then what we're going to do is call quicksort. I already had it copied in my clipboard. And we're going to pass it array. We're going to pass it 0. And we're going to pass it n minus 1, right? And what we're going to do is we're going to print out the sorted array. So we're going to do like system dot out dot print and then we could say sorted array output, and then we go space, and then we can just call print array, and then we can just pass it our array. All right, so let me just see if we have any errors. Just to recap, we're using the Lomuto's partition, right? And for that partition, we want to set our I to low. And what we want to do is first set our pivot to array high, set the I to low, then use J, set that to low. And we're basically just going to use J to iterate through the array. I is keeping track of the boundaries for all the numbers that are less than or equal to the pivot. So you only increment I if and only if you find an array index that is less than or equal to the pivot. And when you do, you want to perform a swap between I and J and then increment that pointer I. Then once you break out of that for loop, you want to swap the pivot with I, because like I is keeping track of that boundary, like I said, and that boundary just after that boundary inside that I would be where the pivot index is supposed to be, and the pivot is supposed to be itself. So you need to swap the pivot with I and then return I. Now then you make a swap function, which is pretty self-explanatory, pretty basic. At this level you should know how to do things like this. So you're just throwing your array in position here into a temporary variable, and then setting that to array position 2, and then setting array position 2 to temp, and that's how you basically perform a swap. And then you have your actual quicksort method, right? And the base case here would be if low, that would have caused an error, if low is less than high. Let me copy this. It's supposed to be in here. And int p is equals to partition. This is the pivot index. So we make a call of partition with our array, our low and our high, and then we recurse on the left, and then we recurse on the right. Left line 28, right line 29, and then we just have a print array function. Not going to go through that. And our driver code here, where we initialize some array and we get the length of that array, and we call quicksort on it, and we print out our values. Now let's print out our values and see. This is a completely unsorted array. Look at it, like begins at 10 to 7, 18. It's all over the place. Now let's see whether this will run and give us a sorted output. There we go. We have our sorted output. 1, 2, 5, 6, 7, 9, 10, and 18. All the numbers here, they're just sorted. And that's basically it. That's how you code up a quicksort algorithm in Java. Just for sanity's sake, let's actually mix this around. Let's make this a 12. Make this a 3, 37. Let's add an extra number, 1, and make this an 11. And matter of fact, let's add a 3 at the end and see how this runs. It's completely random, made that on the fly, made it up on the fly, but let's see what happens. And boom, it is sorted 1, 3, 5, 6, 9, 10, 11, 12, 18, and 37. So that's it for this tutorial, guys. I really hope I was able to bring these points home and sort of explain this in a way that's, digestible, understandable, and concrete and concise. And if you have any questions, comments, or concern, you can, message me or like leave a comment leave a comment under the video, and I'll try and answer you as quick as possible. But for that, and with that, actually, this video is coming to an end, and I'd like to wish you a happy day. And like I said, I really hope you're able to grasp the concept of quicksort through this video. Take care.